Today, we'll be talking about how populations grow. This lesson was made by Jackie Hyanall and Mariah Thrush as part of Ohio University's NSF-funded Boat of Knowledge in the Science Classroom. Watch the video, then pause the video to discuss the questions. Drones are a new technology being used to monitor populations, but how were populations monitored before drones?
Auto takeoff.
For me, this is an entirely new perspective, and it's very exciting. It's just like, opening my eyes to a different view of the whales. I've always felt studying killer whales or any marine mammal is challenging. It's like studying a bird that disappears every time it flies off the nest, right? Every time they go underwater, what happens? We don't know. Well, seeing them from above, we see them going down, we see them coming up, and we see a lot more of their behavior than we do when we're watching them horizontally from a boat. We flew it at 100 feet over the whales. We had more paperwork. The weight of all the permits that we had, I think we were more than the helicopter. We had special flight certificates from Transport Canada and permits under the Species at Risk Act. We even had an FAA permit because the helicopter was built in the States. But that's what it looks like when it's over the whales. You can see how high it is. We didn't see any behavioral reactions from the whales at all. It was one of our concerns and one of the reasons we wanted to test it on the northern residents, which aren't in as bad condition as the southern residents. So we were very encouraged. We could fly it over the whales. No discernible reaction whatsoever. We think this is going to be a very useful tool for being able to monitor populations. The Coastal Oceans Research Institute here at the Vancouver Aquarium, our new center, is all about monitoring environmental change over time and understanding the health of our marine ecosystems. And this is a top predator. So if we can understand how the health and well-being and condition of these animals fluctuates from year to year, we know that tells us a lot about the entire ecosystem that supports them.
Take time now to pause the video and discuss the questions. So, do populations change over time? Populations are dynamic, meaning that they do change over time. They change depending on the resources available to them and how hospitable or inhospitable their habitat is. Why do researchers want to monitor populations? Food resources such as fish are monitored so we don't use them at an unsustainable rate. Other wild populations are monitored to learn their overall health. For example, are they endangered? For possible conservation efforts. Some pest or invasive populations are monitored to manage, slow, or stop their movement into a new environment. Characteristics such as the number of individuals, age structure of a population, sex ratio, that is, how many males to females, reproductive output, or how many offspring per year, resource consumption, number of deaths in a given time period, number of individuals moving into or out of a population are studied to examine populations. I'm sure you thought of other examples. How do researchers track populations in the wild? Other than this drone video, catching and tagging individuals to be caught later, radio tags, and just simply following a population are all used to track a population. What are some ways that nature can change a population? Births, deaths, moving into or out of a population, natural disasters, disease, and so on affect populations naturally, while humans affect populations by pollution, habitat loss, food source losses, and so on. First, let's talk about how populations inhabit a space. Population density is the number of individuals per unit area. In general, there are 3 ways that a population inhabits a space. Random, when there is no pattern to where individuals can be found. Uniform, when individuals are evenly spaced apart. And clumped, when individuals form groups across the area. Age structure is an important aspect of population too. Age structure is the number of males and females of a certain age in a population. It's important to notice that age isn't always measured in years. For flies or bacteria, you can measure age in days or weeks. When filling out your own age structure table, be sure to specify what organism you're recording and to put a time unit on each age class. When immigration occurs, individuals move into an area already occupied by an existing population. Emigration is the opposite of immigration. It's when individuals move out of an existing population. Rarely can a population grow without limits. The carrying capacity is the largest number of individuals a particular environment can support. Limiting factors help to determine the carrying capacity by decreasing population growth. Density-dependent limiting factors depend on population density. Think of this that as the population grows, a certain resource becomes scarcer, which limits population growth. Examples of this are food and shelter. Density-independent limiting factors do not depend on population density, so they affect a population regardless of the population size or density. Examples of this are oxygen supply in normal circumstances and temperature. Changes in population size can be mathematically defined by the equation on the right side of the slide. Notice that the triangle beside the P at the beginning of the equation represents a change in the population. The next term in the equation represents individuals entering the population by births, represented by B, and immigration, represented by I. When individuals enter the population, the size of the population increases. The last term of the equation represents individuals leaving the population by deaths, represented by D, and emigration, represented by E. When individuals leave the population, the size of the population decreases, hence the minus sign before the last term. All populations grow and shrink in this way. So here's an example with fish. Researchers have studied populations to come up with that equation we saw a few slides ago. But what methods do researchers use to study a population? A common method is to find the organism's geographic range, or the area the organism is found. Here, we see the range for the orange-throat darter across several states. Researchers also observe how populations are distributed across their range. Remember, the common distribution types are random, uniform, and clumped. Growth rate, or how fast or slow the population is growing, is also an important aspect of a population that researchers study. We'll talk more about this later. Age structure is also studied by researchers to see how individuals in a population age. This data can be shown in a table, as we've already seen, but it can also be displayed in a graph. Note here that the bars are percentages of the population, not the number of individuals per age group. Back to population growth. There are two types, exponential or unrestricted growth, and logistic or restricted growth. Notice that the pattern of growth shown here by the blue line is different for each type. In exponential growth, population growth continues at an increased rate as more time passes. In logistic growth, on the other hand, population growth slows down as time passes until the carrying capacity is reached. We've already described what the carrying capacity is, but let's now talk about what kind of factors determine the carrying capacity for populations. Before we delve into these factors, remember those limiting factors we discussed? These are the limiting factors too. Competition, a density-dependent factor, occurs when there aren't enough resources, such as food and shelter, for all individuals. Individuals that successfully get a resource will survive and reproduce, while unsuccessful individuals don't survive or reproduce. Predation can also affect the carrying capacity. This factor is density dependent as well. Think about it. If the density of the prey item is high, then a greater amount of predation will happen. If the density of a prey item is low, then predators will have a harder time locating and killing prey items. Parasitism and disease keeps population growth in check too. If the population is large, and also if the population is densely packed together, then the chance of individuals dying of disease and parasites increases. Because of this, it is a density-dependent factor. Unusual or extreme weather, such as thunderstorms or just a drier summer than usual, can affect population size and growth. This problem can affect a population of any density, so is a density-independent factor. Natural disasters, such as tsunamis, tornadoes, earthquakes, and volcanoes, not only kill many individuals in a population, but also greatly reduce resources such as food and shelter. Natural disasters can affect any population, so it is a density-independent factor.